Can we beat quantum potentials with the variational principle? Join us on an exciting journey as we use the power of the variational principle and the Gaussian trial functions to tackle complex quantum potentials. Watch and see how this powerful method can provide upper bounds for the elusive ground state energy. And one of the big concepts that we're going to need here for this problem is this concept of the least upper bound of x. Notice that we can have plenty of upper bounds for whatever we're trying to look for, in this case the ground state energy, but what we're not trying to do is have something so far away out here that it becomes of no physical utility. So we want the closest upper bound to what we call the ground state energy. And thus, we want the greatest upper bound, or the least upper bound, or the supremum, which we'll come back to later. But let's dive into this question. Our problem here gives us a task to use a Gaussian trial function, equation 8.2, to obtain the lowest upper bound you can on the ground state of the linear potential v of x equal alpha absolute value x, and the quartic potential v of x equal alpha x to the fourth. Why do we care though? Well, in this method, it provides the upper bound for the ground state energy. And not to mention, it's really flexible and the simplicity is almost remarkably simple. It's very easy to use. That being said, some might question how good it is, but we see in the case for helium, it got within 2% of the experimental value on a quasi-simple setup versus what it actually is. So, but this leads to a challenge, right? What are the limiting factors of this method? And of course, the book talks about a couple of them, but I'm curious to hear what you have found in your, uh, you know, studies and what you have found in research papers, because there's quite a few more than what the book provides. So, I'm curious to see what you think. That being said, this method is algebraically intensive, so don't forget about the PDF that you can use to follow along. Access it using the link below. And if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. Now, let's get to the fun. Okay, so stop number one then. We have to remember that according to the variational principle, with b as the variational parameter, the upper bound is given as the ground state is lower than the expectation value of the Hamiltonian. Of course, psi's are the trial functions, so they might not actually be the analytic solutions to the Hamiltonian. But we can modify based on the other models we have what we can do for the trial functions. And just to be, oversimplify, but overstate, we need to be normalized. So a lot of authors will just put that this is the normalization factor here, and having that there is just a really good reminder that we're going to need to normalize whatever trial function we choose. And so with this, our task is to find the lowest such upper bound, which will be done by optimizing the variational parameter b, thus minimizing the expectation value. Okay, again, we could have infinity as an upper bound, but that wouldn't do us much of any utility, right? So we want the lowest such upper bound that we're still above the ground state and we have something that's relatively close for what we need. Again, that example with helium, when we got in within 2%, very cool, but still it's 2% higher. So that gives us something to work with. All right, but for this trial function, we know we're going to need to normalize it for anything we do regardless of potential. So let's go ahead and start with that. All right, so that brings us to step 2, where we normalize the Gaussian. And we remember that the inner product has to equal 1. That can be represented as the integral of psi star psi equals 1, of course. And then we see that it will, for b, a real number, a can just be a complex number, but we'll take care of that with the magnitude squared here due to our complex conjugate. And then we're left with a very nice typical Gaussian integral, which is e to the negative 2bx squared, dx of course. And because this is a Gaussian integral, if you look at the PDF, this is the integral from part 1 of the integral series. So we see that that was for e to the negative a x squared, you get pi over a. So our case color coding here, a is 2b, so we just put that down there. And then, of course, if we want to normalize it, we have to isolate a, so we have to divide the square root over, which is what we see here. Of course, this is a fractional power because it's a square root, but it's also in the denominator. So we get a negative 1/2 as the overall power, and we can apply the negative 1 to get the reciprocal here. That's what we see here, which makes sense. If I'm dividing by a fraction, it's the same as multiplying by a reciprocal, and I'm good to go. Thus, after that, taking the square root of both sides, I get my 1/2 power gets demoted to a 1/4 power. And that is what we have seen time and time again for the Gaussian packets. Think about the harmonic oscillator. We had a Gaussian there, and we had a 1/4 for our normalization. More complex, of course, but still, this is on par with what we've seen before. All right, so now that the setup is done and our normalization is done, let's get into the heart of this problem. For the linear potential, we have alpha times absolute value x. Okay, so if the goal is to find the Hamiltonian, what we can do is break the Hamiltonian down into the kinetic energy part and the potential energy part. Oops, looks like we have a typo here. That should not be there, it should just be V. But then that simplifies down because we know the inner product needs to go to T and V. So we can't forget that the kinetic energy operator was negative h bar squared over 2m with the second derivative, and we need to apply that to the right, so the psi trial function. Okay, once we do that, it's a simple calculus, but it is a lot to take care of just due to simplification. So a's can come outside, no biggie. Negative h bar squared over 2m can also come outside, but we see that applying the first derivative to this exponential via the chain rule, we get an extra factor of 2bx. So the negative 2, negative and 2 here cancel, wonderful, and we get a factor of b popping its head out. But because this is a constant, we can bring it out front just like we had with everything else. Good to go. And then I see I'm left with a derivative of a product rule. So I need to take the derivative of the first thing, which is what we see here, leave the second thing alone, which is what we see here, and then take the derivative of the second thing, leaving the first thing alone. Good to go. But we see that we end up with the exponential in both of them, so we can factor that out in the next step. Okay, so all the constants out front, factor the exponential out. Now we're left with this hunker here. So let's go ahead and combine the exponentials, and that's where we get the 2. And then we see we're left with here. So if we redistribute that, no big deal. We just have to split up the integrals into 2 parts, and that's what we see here. Now we have the Gaussian integral that we had from the normalization, and the Gaussian integral that we had to form match. Because of this x squared, we know that we need 2 times n. So clearly 2 is times 1 in this case. And our a factor on the x squared is 2b. So if we plug it into the Gaussian form, we get this here. And this is from the Gaussian table or Gaussian integral 2 in the PDF. And now we're ready to simplify. Okay, so clearly once we plug in a, which we saw was the a squared rather, which we saw was 1 over the Gaussian integral form here, that cancels with what we factored out previously. So we're good to go there, and that's easy enough. Both terms had a pi over 2b from our kinetic energy integral, so we can cancel that with the normalization factor. Beautiful. And then we see that 2b and 2b cancel. So I'm left with 2 minus 1, which is 1 over 2. So then 1/2 minus 1/2, or 1 minus 1/2 gives me 1/2, and hence the 2 I see there. And now that we have the kinetic energy term for this trial function, and we see that it's only the potentials that vary, we can use the same result in part B. That'll save us a lot of time. All right, so now on to the potential that we have here, which was linear. Same setup. We just have to put in that it's a alpha with the absolute value x. Now, absolute value, as you recall, we have a very weird sticking point at 0. So clearly, we have to split this integral up, and that's what we'll see in the next step. Bring all the constants out front. We see that we're still integrating from negative infinity to positive infinity, and that absolute value is going to have to switch over. But because we know that the Gaussian is even and the absolute value is even, the whole integrand is even, so I can double the integral at the price of putting a 0 down here. And that is wonderful. Now, clearly, a quick u sub here, with u being negative 2bx², that will leave us in a much more easy situation than having to use a Gaussian integral table. So we just see we have e to the u here, but our common factor out front is negative 1 over 4 pi. That's just from the substitution. And then we see that 4 and 2 reduce, hence the 2 that is read there. We can bring the negative and 2b out, so that's all the constants out front. Notice that our integration variables, whenever we do a u sub, we can change the variables. So if u is all of this, and you plug in negative infinity, and you plug in positive infinity, the negative outside will turn that into a negative. 0 will go back to 0 though. Nonetheless, we see that we get e to the negative infinity minus e to the 0. And that's setting us up for some good success. All right, so we see that e to the negative infinity yields us a 0, e to the 0 yields us a 1. So we get to cancel the negative and negative out. And thus we see that now we're in a situation where we can plug in the a squared that we found previously from the normalization, which was 2b over pi. Okay, easy enough. Now we notice that 2b can be shoved into the square root, but we have to put a square on it. And we do that because then we can cancel out the numerator with one of the factors from the square here. Cool. And so that brings us to a nice simplified statement of alpha over square root of 2b pi. Okay, so if we want to write this in terms of the total Hamiltonian, which is what we need to write this with respect to b. Okay, because that is the variational parameter. With that, we see that we have the kinetic energy term here, kinetic energy, and the potential energy term here. And then we see that we can rewrite this algebraically speaking, where we can highlight b's dependence in each of these forms. So b was in a square root here, so that would be put to a negative 1/2 power here. And the reason why we want to put it into this algebraically friendly manner is because we know we need to optimize this function by minimizing the variational parameter, i.e. take the derivative of the Hamiltonian with respect to b and set it equal to 0. That's going to be much easier to do when you're in an algebraically friendly manner. So let's calculate this derivative. All right, so Hamiltonian, we see that the b here was just a linear term, so it goes to 1. Get rid of that. Here, we need to do a power rule, so bring the negative 1/2 down, take 1 from the power, and now your life is solely about simplifying this down. Okay, so the negative 1/2 from here turns this positive to a negative, which is seen here. Put the 2 out front of the square root, and now you see that b here we can isolate, and then we could solve for it. So with that, we see that we need to solve for the 1 over b cubed to the 3/2 power, rather, b to the 3/2 power total, and that was due to setting it equal to 0. So push this over to the other side. You see that we get both sides equal now. The 2's cancel. Easy enough. Multiply this term over to that side, divide by this, and we see that we get this result here. And now we can just kind of combine them into something useful. So that gives us m alpha over h bar squared root 2 pi. And to get rid of this 3/2 power, we would take the 2/3 power to both sides. Hence, b equals m alpha over 2 pi and the square root h bar squared, but to the 2/3 power. Again, a lot of algebra and a lot more to come, so be very careful on how you simplify with these powers because it gets messy. So the minimized Hamiltonian, and thus the lowest upper bound, is we have to plug in this optimized parameter into the Hamiltonian, and we get a nice little result. All right, so going back to the Hamiltonian form where we had h bar squared over 2m times b, plug the b in that we found from optimization, plug the b in that we found from optimization. We see that this was the potential term that we had, and we had to make sure it was to the -1/2 power. And now you can start to see we have powers here for all these variables, and then this -1/2. M's are going to end up canceling, alphas, all that stuff. So we have to be very careful. Okay, so to do that, let's color code. The kinetic term gets in purple, the potential gets in blue, and we just see that if I have 2/3 out front or up top for all of these variables, it's the same as 2/3 applied to every single one of the variables independently. So since the 2 pi was to the 1/2 power, you get the 2's canceling. We had an h bar squared here, so 2 times that, easy enough. Because we have a 2/3 here and a -1/3 there, the 2's will cancel, but the negative will remain, so I end up with a -1/3. Again, now we can apply the negative here and flip it due to the reciprocal, and then I can apply the 1/3. But before that, we see that on the kinetic term, this h bar squared and this will reduce, so I end up with 4/3 to the -2. The negative here is just a choice because the h is on the opposite side of the fraction bar, so it reduces the same. Similarly here, we have m, that we get to take 1 from this power, so that's what we see here. This 2 just rides it out here. Of course, our alpha over √2 pi, we turn that into a 1/2. We took the reciprocal here just to get rid of the negative, and now we can apply this 1/3 to all of these variables and combine them again. Okay, so after we're done with all of those, we see that the potential or the kinetic term, we get a -1/3 for the mass reduction, a 1/3 for the 2 pi constant, and a -2/3 for the h bar. Cool. Now we have to do the same thing on the potential side where we have 1/2 times 1/3 since we took that 1/3 power from outside, put it to all the variables inside, and we just do the same thing. Combine, combine, reduce, reduce. And then we see here that this -1/3 gets put in the denominator. This negative gets put in the numerator because we flip what side of the fraction it's on, and that simplifies that side down nicely. This 2 pi to the 1/2, we take that away from the 2 pi after we simplify this. 2 times 3 gives us the 6 that we see there. Good to go. Alpha, alpha, the minus happens again. And then what we see here is actually pretty darn cool. This 1/3 gives this to a -2/3, so that goes up front. Similarly, this reduces down to a -1/3, so it goes below. And I'm able to factor out all of those common terms to the same kind of power. That's freaking cool, okay? And we see that because of that, the 1/2 here that was from the kinetic term, we just have a 1 here from the potential, so we have a fraction that needs to be simplified here, which goes to 3/2. But notice that everything here is to the 1/3 power. So I could pull all those 1/3 out to 1 power, and I simplify my expression to something really simple. So the minimized expectation value is 3/2 alpha squared h bar squared over 2 pi m to the 1/3 power. That's freaking cool. And who would have thought that all this little nitty gritty calculation would simplify to something so neat and compact? That being said, this took a while to type, so I would suggest you use something like Mathematica or Symbol Lab to help you with the algebra stuff because quite frankly, if you're comfortable with it, that's just going to eat up a lot of your time. The computer's going to be chugging through it a lot faster than we can. Use it to your advantage just to understand where they might have these simplification acts and understand that sometimes it's not going to come out in the exact form. Algebra will make or break all of your simplifications. So now that we have this minimum, let's go back to the picture that we had seen previously, or rather a variation of it. So here's a graph of a sequence where the blue dots are just a sequence. Anybody who's taken an analysis class has seen this before, but not everyone has, and this is very important to us. The dashed line is the limit of the supremums. Sup stands for supremum, and that would be SUPREMUM, and this is the lowest upper bound. We see it's the lowest one that gives us everything we need to know about how the sequence goes up and down. This is the same thing, but for the greatest lower bound. And trust me, it's a whole tongue twister that gets you all confused until you hear it enough times. This is known as the infimum. 𝐈𝑛𝐹𝐼𝑚𝑢𝑚. Close enough. And so again, the whole point here is that what we don't want is something up here, right? If these are the ground states that we're measuring, ground states, and we have something up here, of course we could always pick this and then something above it, but that's not going to get us anything closer to what we want to do in minimizing this distance from the ground state that we measure experimentally with the theoretical results. So we want to pick the lowest such upper bound to get us the closest here to our ground state. And that's what the goal. So now that we have this kind of foresight with us on this example, we can go ahead and speed through the next part, which is of the, I believe, the quartic potential. So let's dive into that. All right, so yep, diving into straight to part 4, or stop number 4, the quartic potential, which again is another even potential, so we have something cool there. Thankfully, we don't have to find the kinetic term now since we already did it last time and nothing about the kinetic term changed for this trial function. But it did, the only thing that changed was the potential. So we had alpha x to the fourth. Cool. So let's plug that into our form. We see that we get alpha x to the fourth, all constants out front. Now we see that we get a nice Gaussian function again. Again, using the form Gaussian 2, we see that we have 2 in here, but that 4 breaks down into 2 times 2, right? And that 2 is the n factor that we have. 2b is the a in the integral table. So then we just plug it into the form. It gives us 1 times 3, 2 to the 2, a to the 2, but a is 2b, and we get our square root again. But again, we saw that a squared from the normalization was 1 over the square root, so cancel, cancel, and we get a cute expression here. Much more simpler on this time. Oh, excuse me. So, rewriting our Hamiltonian in terms of an algebraically friendly manner, we get this expression here. H bar squared over 2m times b plus 3 alpha over 2 times 8b to the negative 2. Although it's 16 here, we know we're going to have cancellations soon because of the derivative. So writing it in this kind of pre-factored form is just a hindsight type deal because we know we're going to end up canceling them. So let's take the derivative, set it equal to 0. We see that the b factor here was linear, so it goes away to 1. We get a negative 2b to the negative 3 from the power rule. So that negative 2, or that 2 and that 2 cancel, hence the prefactor. And then we see that we just get a negative sign here. All right, so because we saw that we had a cancellation of this 2 on the last round, another prefactor of this 8 is going to help us. And when we set it equal to 0, we shove this to the other side. That's why it's over here on the equal sign. And so the 2 and 2 cancel. And we just do this because hindsight tells us it'll make our life easier. All right, so isolate b, multiply this over to this side, the left-hand side, divide the left-hand side to the right-hand side. We get this nice compression here. Simple and sweet. But again, to isolate b, we need to take the cubed root, hence the 1/3 power. And once we do that there, we can simplify down once again. Writing 2 as 2 to the 2 is another kind of hindsight check because we know we're going to have to distribute that 1/3 to everything, and 2's tend to cancel in this scheme. So that brings us to the lowest upper bound is we have to plug in the b value that we just found from optimization and run through the whole simplification process once again. Okay, so this 16 here is 2 to the 4th. Again, we're dealing with powers, so let's bring it to the lowest root, lowest base, and to the highest power, and then simplify with power rules. I'm not going to go through all the power rules again because I think that will beat you to death in a boring sense, but we can see all the work here. It's just amazing to me how this works out so nice to where we can have that 1/3 factor from both of them factor out so nicely. So let's continue to simplify this on the next slide. Okay, so once again, we see that we get all our factors pulled out, so we can find the common ratio here. The 3 over 3 just came from that 2 here that we left off. And that simplifies to 1, of course, so we just get 1/2 here. Verified there. And then we see again that all of these have some kind of factor of 1/3 in their power, highlighted in red, so take it out. And of course, we see that that's 2 to the 5 there, which of course we can break up into 2 cubed and 2 squared. That way we can pull this out of this 1/3, and then we have 1 over 2 times 3 halves. That gives us the 1/4 here, the 4 here, and we simplify down to something really clever. So it's not that hard of a theory, so to speak, as compared to making sure we had all the states accounted for in the perturbation theory and degenerate perturbation theory, but it is tedious. So use the computers to help you because no one wants to sit here and type out 1,000 lines of algebra, okay? But nonetheless, these are very nice results, all things considered. So this is a very cool principle. And when we get into the ions and the helium atom and the molecules, this will be definitely more forecasted in the more applications. Right now, it's just you're trying to get a feel for the theory, but once we get to see some of the applications, it's actually pretty darn cool. All right, so thanks for listening to my yabbering about that. The more I look at the stuff, the more fascinated I become at it because there was some real heavy insight and we don't necessarily appreciate the insight that people who first started this theory, uh, all their trial and error, putting it into a simple book. Hindsight is definitely beneficial. So I'm just always amazed by how these things came to fruition in the first place. Very, very cool. That being said, with all the travel and the storms recently, uh, you know, making the stuff has not been on the priority list and people still support. So I want to give a massive thank you to all my supporters for making this possible. I am definitely extremely grateful for your support. And if you'd like to support and see more, you can become a patron for yourself too. Keep us up to date with how your studies are going, what you're studying. There's been a lot of cool things I've learned. And one of my friends just sent me a very cool playlist about functional analysis and quantum mechanics, and I've been looking at that nonstop. And this kind of stuff, where that opening picture had the weird little subsets on that line with the lowest upper bound and the greatest lower bound. Those all come from functional analysis and Borel sets and all the kind of measure theory. Very important to quantum mechanics that we can't get into on the ground level, but definitely get used to seeing that kind of language because it will be at the next level. So, that being said, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious and stay healthy.